So you can have all the cold air you want come pouring out of the gorge, but it's not going to reach the west side. Which I kind of like, although one year we got real snow about this deep in the street in front of my house. And I'm from Montana. I'm out there shoveling it so people can get by. Like, why are you shoveling the street? So you don't get high-centered on the snow. I won't get high-centered on the snow. I got a minivan. 20 minutes later. Can you dig my minivan? Okay, Brittany House. Robert Thompson. All right. So if you know anyone that's normally here and they're not here today, let them know that this class is being taught tomorrow at 2 o'clock in EB 93. Because I don't have anything to do with the weather, but I can tell you that paging is the hardest topic we will cover this term. And just so you all know, if you all want to have another shot at and see the material, you can always come to class tomorrow as well. You might have to sit on the floor, but you can attend either or even both classes.
What time?
2 o'clock in EB 93. It holds 10 fewer than this room. So, today we're going to start talking about a very modern virtual memory system called paging. Paging has been around forever. Okay, well, not quite forever, but it's been around for a very, very long time. And now it seems to dominate. The Intel architecture presently still requires that you use segmentation. You have to use segmentation in the, at least up into the Core i7. I don't know if Core i8 was recently released. Somebody told me it's either that one or the one coming after it, where they may make grouping and segmentation optional. When we get done, sort of in the next class period, I'll tell you how we combine the two of them. And if anybody wants, I'll set up a time we can go off into a conference room, and I can show you exactly how it's done and how it's set up in XV6, because XV6 uses both segmentation and paging in a way that segmentation looks like it's not there. We do the equivalent of turning it off. And that's what Linux does, that's what Solaris does, that's what standard Unix does. Okay. So there's a couple of tricks we do when booting to make that happen. Now, we saw before this idea that the CPU now going to emit a virtual address. Okay. Why can't the CPU emit? Why on a modern system? Why in a modern system with modern compilation and linking, why is it that we're not emitting physical addresses? Does anybody have an idea on that?
Because you don't want to interact with the hardware itself.
I'm sorry?
You don't want to interact with the hardware itself.
Yeah, I mean, it's basically that. Okay, basically what's going on here is that the process itself is going to live in a virtual address space so that it can't talk directly to the hardware. Okay. Also, when are virtual addresses assigned?
At compile time?
At compile time. Actually, it's what part of the compilation process? The linker. Okay. So the linker is going to assign these virtual addresses. And that's cool because the compiler and linker with compilation process is going to set us up to work in that magic virtual address space. And so it gets to make, it gets to assume it owns that virtual address space. It can set things up however it wants, okay, theoretically. Also, we don't, at compilation time, do we know what other processes are in memory? could we conceivably know where in physical memory the parts of our process will be? In fact, we don't even know how much physical memory though will be on that machine. All right? So we're going to be emitting virtual addresses. We have no choice in using a virtual address system. But hardware, our memory, is addressed with physical addresses. And we've got this memory management unit in between. The memory management unit for a paging system is more complex, and it needs actual data in physical memory. Okay. So, once again, how often do we access memory? Or do we need to translate virtual to physical memory addresses?
All the time.
All the time, okay. Let's be a little bit more specific than that.
When we need more space.
When we need more space, certainly.
When we reference the address.
When we reference an address, how often do we reference an address? Like, for example, how often do we use the instruction pointer?
A lot.
Yeah.
All the time?
Every instruction. So that's all I was trying to get at. It had to be all the time, kind of gives you a little. But now, there are things that we can do in hardware to optimize this so we don't necessarily have to translate virtual addresses every time, but those are beyond what we're talking about. So we're going to go under the assumption that the MMU has to do a translation every time. It makes it easier for us to see. Unless you guys want to start adding in algorithms for caches and cache misses and prefetching. Anyone want to do all that? You sure? Okay. It'd make for a really wild test. So, we're not going to do that. It's just unfair. Instead, we're just going to say that virtual address goes to the MMU is going to translate it, and then we're going to go and get it. We're not even going to allow physical memory, in a sense. We're not going to talk about caches between the CPU and physical memory, except for one that's located inside the MMU. Okay, so that's a specific class we'll be talking, cache that we'll be talking about today. So, one of the things that it's very useful to know in memory systems is that the disk is memory. Okay. How many of you think of the disk as memory? It's kind of weird when you think about it. You're like, well, yeah, duh, obviously, Mark. Okay, it stores stuff. It's a specific type of memory that we call persistent. What do we mean by persistent? It'll still be there even after you turn the machine off and turn it back on. So it will withstand crashes, power cycles, power failures, little brothers and sisters with Coke, things of Coke with no lid on them. How many of you have lost a keyboard to a drink that should have had a lid on it? Okay. So, we can think now of a process as being bigger than memory, or the amount of work we want to do being bigger than memory. And paging is the easiest place for us to describe this, so I've delayed it to here. We can have this whole concept with segmentation as well. And when we're done talking about paging, talk about how it's done in segmentation. It will be so trivial that you'll look at me and go, well, duh, why don't you tell us that first? Well, because I would have told you all the stuff that I told you in paging first. So instead, we're going to look at it here. So processes now are going to be comprised of things called pages. Okay? We've seen the paging concept before. It looks very much like fixed size segments. Okay? And in a sense they are. A page is a fixed size segment. What was the beauty of fixed size segments? No external fragmentation. So that's what we're going to get with paging. It turns out we're going to have a bound, a very small bound, on internal fragmentation as well. Okay? So it turns out that of the systems that we've looked at, paging is going to give us the best use of memory, and we're happy about that. Why?
Because it's fast.
Because it's fast. I'm not sure what you mean by that.
It's efficient.
What do you mean it's efficient?
It efficiently uses the CPU time.
It efficiently uses the CPU. Why? Because we can get more.
We can do more processing of things.
How about we can put more process into?
We can put more process into memory.
So we can put more process into memory. Very good, thank you. And what's the benefit from that?
More concurrency?
More concurrency, potentially.
Higher chance the CPU has something to do.
Higher chance the CPU has work to do. Okay. So we're going to be very space efficient, which means we're going to get more processes into memory. And we're going to start talking about how the fact that we don't need all the pieces of our process in memory at any one time. We don't need them all. We can push some of them out to disk, even though you're executing somewhere else in your process. You could be in the CPU, and only a small fraction of your process is in memory. The rest of it's on disk. Yet you can't tell most of the time. Okay? Kind of see the complexity that we're walking up against? Where are my pages? It's kind of something that we can ask. And sometimes we can tell you where they are. Okay? So, disks, big, cheap. All right? They're big, they're cheap, and what else are they? Slow. Okay? So adding the disk in here potentially adds unbearable latency. But for now, we're going to bear it. We're not going to talk about some of the techniques for reducing that latency. We're just going to recognize that going to the disk has very high latency, and therefore we want to avoid, okay, and when I say avoid, there's a specific type of avoid that we're going to go for, and we'll talk about that later. Okay. So, we've got this disk. Think of this now, we have this big, huge disk, which is just a linear array of disk locations. And in there, we've got a process. Okay. There's different ways that we can allocate this space on disk for our process. We can allocate and say, oh, your 2 gigabyte process, here we'll give you 2 gigabytes of space. Not efficient, okay? Not really efficient at all. We could go up there and say, oh, you got this much of your memory in use, of your 2 gigabytes, let's give you that much. If you need more, we'll give you more on disk. We can certainly do that. So there's different strategies for allocating the space on disk. We're not going to talk about that. We're going to assume that if a page in a process has been allocated, that it exists somewhere on disk as well. What that means is, where's the good copy of the data? Okay. So let me back up. Where is the actual data stored? Is it stored in physical memory or on the disk? Turns out it's going to be the disk. Okay? It's because we could kick pages out of memory. We're going to see. So we're going to wind up seeing that, gee whiz, physical memory is what type of structure for the disk? Does anybody have a suggestion on that? we can look at physical memory as a cache of our disk. All right? So, that means is, like any other cache, is that at any particular point in time, physical memory has some subset of the data on disk. The place where we're going to be putting these pages at, which is not the original files, places where we can put them while we're moving them in and out of memory to make our process run, we're going to call swap space. Okay? And the action of moving them in and out of memory, we're going to call paging. If we do it with segmentation, we call it swapping. But we'll leave that for right now. So now, we can say that a virtual memory or process is bigger than physical memory. And certainly if we have lots of processes, it's going to be way bigger. So, my process on Linux is, on 32-bit Linux and x86, 4 gigabytes. Okay, 2 goes to me, 2 goes to the operating system. Or on some systems, 1 gigabyte goes to the operating system and 3 go to the processor. So now we have this idea of, not all of it will fit. Okay? Not all of it will fit. And we go through here and think about physical memory. We get talking about what will fit, why does it have to fit. We need to know something about terminology. Inside of our virtual address space, we have virtual pages. And part of the virtual address is the virtual page number. Okay. Now, when we have that virtual page in physical memory, we want to distinguish between the virtual page itself and where it's stored. So what we're going to call the locations where we put things in physical memory, we're going to call them page frames. And they look just like a frame on a painting. It's the same size as our painting, and we store stuff in it. But we can take things out and put different paintings in there, can't we? Right? So this page frame, at any particular point in time, a page frame may hold exactly 0 or 1 virtual pages. All right? If the page frame contains a valid virtual page, it's in use. Otherwise, it's free. Now, I think we've already decided that nobody wanted to remember CS201, or at least not with affection, right? We're going to go back to CS201 and talk a little bit. And it comes down to, why does caching work? Right? Why does caching work? If programs, processes run around just randomly accessing different parts of the process, we'd have no ability to predict what pieces of our process it would be referencing, could we? Okay. And it turns out that for almost all programming languages, we do have the ability to predict. Not with 100% accuracy, okay, but good enough. So this is what's going to happen. We're going to have, let me grab the stack of papers over here. Here's a stack of paper. Okay. We call each piece of paper a page. And this is how it works in page virtual memory. Each page is the same size. Each page may or may not have the same information on it. Right? And we could look at individual pages by saying the 3rd from the top, the 24th from the bottom. Okay? So this is what it's going to look like. Pages, the way we're going to look at them, are 4 kilobytes in size. All right? How many of you are curious as to why it's 4 kilobytes? Nobody's curious as to why it's 4 kilobytes. Okay. But it can also be a megabyte.
This is virtual.
This is virtual. Actually, it turns out we have to take and we have to do some kind of attention here. We're going to make our units of transfer to and from the disk pages, and they're going to be contiguous block of memory. And disks are slow, so we don't want to have to go out there and just write 1 byte. So we want to try to make the writing to the disk as relatively cheap as possible, as we're going to amortize the cost. So the bigger the chunk that we write, the lower the cost, because it's going to be contiguous on disk. And positioning on diskette is the slowest operation. Now, if the pages are too big, okay, then we have other types of problems. Okay, it could be that that to push 1 page out takes a very long period of time, and because of that, it impacts the performance of our system. So we've got 4K pages being used in XV6, and most systems will use them. They also have things called super pages, which we're going to ignore. We're not going to talk about super pages at all. And so we've got this process now comprised of 4 kilobyte pages. So here's an interesting question. If I have a 4 gigabyte virtual address space, how many pages is that? I'm going to guess 4 million. I'm going to guess 1 million. Okay? 1 million pages. What do you guys think? Should we do a base bounds? Well, they're fixed size.